LU factorization. We know how to solve triangular systems of equations using forward and back substitution. Consider A lower triangular matrix and B an upper triangular matrix. Their product, A times B, is neither. Can this process be reversed? A key insight is to think about A times B as columns of A times rows of B. If we partition A into its columns, we call them C1 and C2, and if we partition B into its rows, we call them R1 and R2. We can think about A times B as C1 times R1 plus C2 times R2. And we can verify this in Julia to see that C1 times R1 plus C2 times R2 is the same as A times B. Through a step-by-step example, we're going to factorize matrix M. Step 1. We define C1 and R1 to be the first column and row of M respectively. This is C1 and this is R1. We also define the first entry of the diagonal of M to be a variable called pivot. Then we divide C1 by pivot. This makes the first entry of C1 to be 1. Then we subtract C1 times R1 from M. Notice that C1 times R1 is a 3 by 3 matrix, so the subtraction is defined. The result will be a matrix with 0 in the first column and 0 in the first row. Then we define a new variable, temp, to keep the result for the next step. We can do the calculation in Julia as well. We define pivot, C1 divided by pivot, and R1, and we get our temp variable. Step 2, we start from the temp variable and we define C2 and R2 to be the second column and row of temp respectively. We define the pivot to be the second entry on the diagonal of our matrix, and we divide C2 by pivot, which makes the second entry 1. Again, we subtract C2 times R2 from temp. This will result in zeros in the second column and the second row. And we define the results again to be our new temp variable. Again, we can verify this in Julia. Step 3, we define C3 and R3 to be the third column and third row of temp. We define pivot to be the third entry of the diagonal of our matrix. We divide C3 by pivot, which makes the third entry 1. C3 times R3 results in our temp matrix. In other words, temp minus C3 times R3 equals 0. Therefore, M equals C1 times R3 plus C2 times R2 plus C3 times R3. We can use the vectorized notation by concatenating C and R variables. And we can verify the last step in Julio to see that temp minus C3 times R3 results in 0. We learned that concatenation of C1, C2, and C3 forms a lower triangular matrix, which we defined it as L, and the concatenation of R1, R2, and R3 forms an upper triangular matrix that we define it as U, and L times U will produce matrix M. So M is the product of a lower triangular matrix and an upper triangular matrix. We can verify that. We stack C1, C2, and C3 to form L, and we use R1, R2, and R3 to define U, and we recover M by L times U. In general, if we have a square matrix and we subtract first column divided by its first element, assuming it's non-zero, times the first row, this will zero out the first column and the first row of the matrix. This was the process we repeated to eventually get the zero matrix and decompose our matrix into a lower and an upper triangular matrix. We can use LU factorization for solving linear equations. We wish to solve A x equals B. If we can factor A into L times U, then we have LUX equals B. Then we can define Y to be U times X. Then we get two equations. Ly equals B, Ux equals Y. We first solve for Y via forward substitution because L is lower triangular. Given Y, we solve for X via back substitution because U is upper triangular. Next time, we're going to see LU factorization with row permutations.